Okay, in this video, one of the applications of linear optimization can be found in any kind of blending problems. So this is a very common field, especially in chemical production facilities or any kind of mixtures that you're putting together in chemistry or any other field. So in this example, we do have a bird seed company which specializes in food products for birds and other household pets. In developing a new birdseed mix, company nutritionists have specified that the mixture must contain at least 13% protein, 15% fat, and no more than 14% fiber. The percentages of each of these nutrients in 8 types of ingredients that can be used in the mix are given in the table below, along with the cost information. What is the minimum cost mixture that meets the standard nutritional requirement? So these are the controllable inputs that we have, right? Sorry, uncontrollable inputs that we have, mainly the parameters that are given to us, right? So from, let's say, the ingredient is per pound, okay, per pound of sunflower seeds, we do have 16.9% protein, 26% fat, and then 29% fiber. And then its cost is 22 cents per pound, okay. If you use per 1 pound of the sunflower seeds, we are going to get 16.9% of that 1 pound is protein. 26% of that 1 pound is going to be fat, and 29% of that 1 pound is going to be fiber. We are allowed to use all these ingredients, okay, in order to put that mixture together, okay. And in that mixture, our restrictions are that that mixture must contain at least 30% of protein, 50% of fat, and no more than 14% fiber. We are allowed to use these 8 types of ingredients. So what is the minimum cost mixture that meets the standard requirement on this mixture? Well, again, the first step, just to remind you, is to define the decision variables. The second step is to put together the objective function by using these decision variables. And the third step, we have to explain what our constraints are, and finally we have to convert them into math. If we fail in any of those steps, we go back and update our decision variables. Well, first step is to put together our decision variables, right? So how to define our decision variables in this example? We are allowed to use 8 types of ingredients, but what we don't know is how much to use from each, right? So that might be a really nice way of defining our decision variables. So actually, yes, so we do have one decision variable for each ingredient, and those are going to represent the amount of pounds of ingredient I to include in 1 pound of mix. So for example, here we do have I changing from 1 to 8. So x1 is going to stand for the first ingredient, x2 is going to stand for the second one, all the way up to x8. Okay, if we go back to our table, so x1 is going to be sunflower seeds, x2 is white millet, x3 all the way up to x8. That's a good start. So let's see whether we can formulate our objective function value, objective function itself. Again, the objective function is that we would like to get the minimum cost in that mixture. So yes, we can by using these decision variables, because those are just the amount of pounds of ingredient I to include in 1 pound of mix. So we are talking about 1 pound of mix here. And the first constraint to consider, I will explain these constraints later on, but this is related to what you see here in the objective function, is that if you add all the values of our decision variables together, we say that it has to be 1. So therefore, these x's are in percentages, right? So all these x values are going to be between 0 and 1. The maximum value can be 1, the minimum value can be 0. So we already made them percentages, so or it's just going to be the amount of mixtures that can be used in 1 pound of mix, as described in this decision variable. So we are safe to use x1 all the way up to x8 decision variables in the objective function. If you multiply the cost values with them and add them together, you will get the total cost, right? So this objective function is just going to give you the total cost value, which is fine. Second step is completed. We can represent our objective function value by using the decision variables. That's good. And then our first constraint is to make sure that these values, decision variable values, are going to be between 0 and 1, so that we can deal with the problem of putting together 1 pound of mix. If you remember, we do have some lower limits and upper limits on protein, fat, and fiber. So let's take a look at what those are. It says that the mixture must contain at least 13% protein, and we do know exactly for each of these ingredients, we do know exactly how much protein, how much fat, and how much fiber they contain. So we can control the protein usage, right? So if you multiply, for example, x1 by multiply this with the related protein percentage, you're going to get the protein amount we are getting from this sample over seeds. And we are interested in finding total protein, so you just keep doing this, right? x2 times 12% all the way up to x8 times 11.9%. This should give us the total protein amount in that mixture. Basically, this left-hand side of this constraint is going to give us total protein amount in mix. And we want to make sure that this is at least 13% of that mix, right? Okay, so let's keep going. For the fat, we do have a very similar constraint. It says that for the fat, you have 15%. All we have to do is to change numbers. This time we are going to use these percentages right here and then represent the fat constraint, at least 15%. Fiber, it has a slightly different wording. Still, we are going to control the fiber in this mix by utilizing the same approach, but the symbol is going to be, this is an upper limit, not a lower limit on fiber, so we just changed this greater than or equal to less than or equal to constraint. So this is the non-negative restriction that says we cannot simply use negative amount of percentages from each ingredient, right? And this should be the mathematical representation of our model. Well, what's the optimal solution to this one? Well, simply we cannot solve this by hand, therefore we need to go to Excel to optimally solve it. Okay, so you do have the blending sheet here. If you make this full screen and get closer to your problem, I will show you how to use this Excel template for this. So go to view, zoom to selection. Okay, so it's better. So we do have the data, protein percentages, fat percentages, and fiber percentages already given for each ingredient, and we do have the cost information. So as you can see, the amount is left empty, so I'm going to use this for my decision variables, okay? These cells are going to hold how much ingredient I'm going to use for this mix, okay? So these are the minimum requirements for protein and fat. There is no minimum requirement for fiber, but there is a limitation, or the upper limit requirement for fiber. There is no upper limit requirement for protein and fat. Well, if you do have one, you can add them here, no problem. Remember, I have to control the sum of this total ingredients, because that's what my problem said, right? In order to put together the proportion, I have to add them up and make them equal to 1. Okay, this is what it is. So it just sums these decision variables, x1 all the way up to x8. So here in this cell, I control how much my total value for this mix is going to be, right? It's just the sum product of this array with this array. So it's going to product them and then sum them together. It's going to give me my objective function value. The protein percentage is going to be, it's just the multiplication of this with these decision variables. It's just to give me what I have here as a requirement as a left-hand side of this constraint. So it's going to be the total protein in mix, right? It should be greater than or equal to 13%. Well, how do I get the left-hand side? By this way, right? Similarly for fat, I do have the sum product, right? And I do have one for fiber as well, okay? Let's go to Excel solver, okay? And then you have to set objective to min, right? We would like to minimize total cost. Total cost is written right here. By changing which variables, these are my decision variable cells. Go ahead and add my constraints one at a time. My first constraint is the proportion constraint, so the sum of these x variables must be equal to 1. I'll just type 1. Click add. I do have a minimization requirement for protein percentage. Where do I keep my protein percentage in this mix? So it is right here. It is B17. Should be greater than or equal to 13%. I do have a very similar constraint for fat, greater than or equal to, sorry, I have to update this. So I do control the fat amount right here, B18, should be greater than or equal to actually 15%. Finally, I do have an upper limit constraint on fiber, so I select fiber usage here, less than or equal to the upper limit value. Okay, that's about it. I do have 1, 2, 3, 4 constraints. Is that right? Yes, I do have 1, 2, 3, 4 constraints. I have to make sure that my decision variables are non-negative. By checking this box, that's correct, and I hit solve. Says solver could not find a feasible solution. We'll see why. Go to solver one more time, go to options, maybe we should use automatic scaling. Okay, and then hit solve. Again, the same problem. So let's see what's wrong with the solution. So it says that the total cost is 15 cents, the protein is 16%. This is the min requirement, which is good. This is the min requirement. Oh, okay, this is the one that's not conforming, right? So with this current fat percentages, what you see here is that currently the fat percentage is 14.89, and then the minimum amount is 15% only. That's why I couldn't get any feasible solution to this problem. With this current data, there is no feasible solution for this new mix. Well, the conclusion is that this is your best shot, but you're not going to get a feasible solution. What you can do is you can update this minimum requirement to, let's say, 14%, right? Update it to 14%, and let's go to solver and let's see what happens if you do that. There you go. It says solver found a solution, all constraints and optimal conditions are satisfied. Basically, what changed here is that now I can freely satisfy the minimum requirement for fat. If this is an FDA requirement, you cannot do that, right? You cannot play with the lower limit on that constraint, on that mix. But we just did it for the sake of finding a feasible solution, optimal solution. This is how we do it.